Okay, all right. So welcome you all the participants once again. This session will be taken by me only, and the title of the session is Optimal Control of Wind Power Generation Systems. Since its name suggests that it is very much conventional title, and since as I already discussed in the last, session or in the inaugural session also, that we are having the participants from the various disciplines. Some of the participants are from, from computer science or some other background. So they might have not much knowledge of, deep knowledge of kind of wind systems, which are actually being integrated with the grid and all. So that's why I have just taken a simplified title, and a little bit complex thing is that the kind of optimal control, how an optimal control can be incorporated into a wind system so that we can extract the maximum power out of a wind turbine systems. So coming to the outlines, I hope my slides are moving. Is it changing? I think so. So this is the outline. Is it okay?
Yes, sir.
Okay, all right, thank you. So this is the outline of my presentation. The people who are from the electrical engineering background or from power system background, they are very much well known about these content. The the advanced thing which I need to point out here is the damping control through LQR at the end. You may see here in the slide also. But rest of the things are very much conventional, and it is just for the information, or I must say, just kind of a general information for all kind of participants. So here is the outline. I'll start from the introduction section, and then I'll tell you about the various kind of wind energy conversion systems. In that one, I'll talk about the various kind of generators also, which are actually used with the generation through the wind. Also various kind of controllers which are conventionally available with the wind power systems, or will also be discussed in detail. And then later on I'll present some kind of stability analysis, or I must say small signal stability of a doubly fed induction generator type of wind power system. And then later on I'll discuss on some advanced way, that is the optimal control, which is basically linear quadratic regulator control of the wind power generation system. So these will be the outcome of my presentation for this session. So here is the introduction, and this is very much conventional. So the generation of electrical power from renewable energy sources has been increased significantly in recent years, as we have also discussed in the last session, the inaugural session. And as far as the generation of electrical power through wind is concerned, we are at the fifth position. So we are fifth largest installed wind power capacity after China, US, Germany, and Spain. So as of, although this data is very much, I mean, old. So, but if you talk about this one, say installed capacity of wind in India is about 40 gigawatt earlier in 2021, but it has increased now and it is about two times of this one. About 82 gigawatt of power is being integrated with the grid in 2025. So you can think of that within 4 or 5 years, it has been increased in double. So earlier it was only 40, and now it is about 82 gigawatt generation of wind is being generated. So that's why it must be discussed in detail by every researcher, every academician, and kind of policymakers also. So at the end of that, this is also in older data that Ministry of New and Renewable Energy has set higher goal for the with the generation of wind power. Out of the various kind of wind power generating mechanisms, or the kind of structures, WFI induction generator based wind power generation is very much prominent, and that's why about 70 to 80% of electrical power using wind are being generated through these kind of generators. DFIG, actually doubly fat induction generators. So most of the power rated wind power generating plants have these kind of generators. While if we talk about some small scale wind based generation, then the PMSG, permanent magnet synchronous generators, are mainly used. This is because of the use of higher use of this DFIs is because of its flexible control, it variable wind speed, low converter rating, as well as reduced turbine stresses. Actually, when we are using this DFIG, then there is some mechanism with this kind of generator that we can feed some voltage to the rotor of that generator so that it can be flexibly controlled. So since the change of wind speed is not in our hand, we don't have the control over the flow of wind. So with the changing structure of the wind, how to get the maximum power out of that? So that can be happen with the help of these kind of generators. So that's why these are very much prominent. Very much kind of research is going on in these control of such kind of generations through this wind. Very much conventional controls are like MPPT control, then damping control through various techniques. Then there is the pitch control. Then frequency regulation is also being associated with the DFIG based systems. Along with them, there are another advanced techniques like event triggering techniques are also there. Then adaptive control of wind based generation is also there. Then some estimation based control, then kind of optimal controls. So these kind of controls can be designed and put the voltage to the rotor of that generator, that means the WFI induction generator, so that we can have the desired output out of that system. So this is the basics or the kind of introduction about this presentation. Now here is the very much conventional way of generation of electrical power out of wind. So it can be seen over the picture that it's very much simplified. Is this is kind of a layman kind of view. Everyone can understand only by just looking onto the picture only. So as soon as wind flows, this kind of structure, kind of fan, which we usually talk it wind turbine. So because of the flow of wind, this wind turbine rotates, and there is a mechanism, mechanical drive unit is there, uh, which is uh, which is making couple to the generator with the turbine. So with the rotation of the turbine, definitely that generator rotor will also rotate with that, and it will work like a prime mover or a mechanical input power to the generator so that its rotor will rotate, and ultimately because of the rotation, that generator converts that rotational mechanical power into the AC electrical input power, output power. It may be AC or DC depending on the use of generator. What kind of generator we are using here, that depends on that. So since there are various kind of controls with the wind systems, so that's why here one arrow is shown inside the generator, which actually shows the various kind of controls to be implemented over the generator. So control and supervision can be put over the generator as well as the turbine also. We will see how we can have some control over the turbine also. So there are kind of two type of conversion of energy. One is from the kinetic energy available into the flow of wind, that first converted into the mechanical rotational energy by the wind turbine, and then later on that mechanical energy will be further converted into the electrical one by this generator. So there are two kind of energy conversion. First one is kinetic to mechanical, then mechanical to electrical. So this is very much a basic structure and everyone can understand simply by just looking onto the picture only. So that's why one can understand that the important component which are basically present in the wind-based systems are the wind turbine, which is one of the prominent part. Then the coupling mechanism, there is one gearbox in between them, generator and turbine. So that is also one of the important part. Then another one is the generator. So which should be selected is according to our need, or the according to the availability of the wind and all. So this was the very basic about the wind, and then coming to the wind turbine and wind power extraction. Since we have talked about that that wind turbine is nothing, it is a kind of structure, is kind of fan kind of thing, and because of the flow of wind, that the turbine will rotate and it converts the kinetic energy of the wind into the mechanical one. Now, but since everyone, I hope that many of you are thinking that it's a very basic kind of structure of wind turbine is there. But I wish to tell you that the design of the blades of a wind turbine is very much complex. I mean, there are various kind of parameters which actually integrated with the wind turbine blade design. So actually, in a wind turbine blade, if you have seen somewhere the structure of a wind turbine, you can see that a wind turbine blade is something like that. That it is it has lower diameter at the near the hub where it is connected. Since it is kind of fan, so near the hub, I mean where the blades are connected, that is known as hub. So at the hub, the diameter of the blade is very smaller. Then in between somewhere, there are larger value of that the diameter, or I must say chord, that is known as chord. So higher cross-sectional area chord is there, and at the end you might have seen that a very thin, very lower cross-sectional area blade is there at the tip of that blade. So why this kind of structure of blade is utilizing. So I wish to tell you that the if you are cutting one blade and see the cross section of that blade, then that is known as aerofoil or airfoil sometimes. So that aerofoil structure is very much important. Actually, that aerofoil structure decides the drag and lift coefficients. So accordingly, the force which is actually been converted into the mechanical power at the shaft of that turbine will depends on very much depends on the lift force and the drag force. So although I am not going into deep about the design of the blade, but since a wind turbine actually takes the rotor geometry, that is lift and drag parameters, which actually been um, get from the testing of a aerofoil or the blade, and then the input energy in terms of wind, and then there is the generator speed, or I mean turbine speed, as well as the pitch angle. Pitch angle is another thing which actually the angle of the blade with respect to the flow of air. So that exactly gives the pitch angle. So this pitch angle control is also very much important. So actually a wind turbine, you simply mathematically you can think of that a wind turbine is nothing. It is a kind of black box which actually take these much of parameters and gives the output power. So this output power is in terms of these left and drag coefficients, as well as the wind speed, and then generator or the turbine speed, as well as the pitch angle. So these parameters, with the looking onto this picture, we can see that the output electrical power, or definitely that the mechanical power which comes out to be the wind turbine will ultimately reflect into the electrical power through the generator. So definitely that electrical power depends on the mechanical power, and then mechanical power depends on these many of the parameters. So that's why we usually say that the output power of a wind power generating system depends on the wind velocity, obviously, then air density, how the density of the air is there present, and then size of the wind turbine, as well as the characteristics of the wind turbine. This is very much important, the characteristics of the wind turbine. It may happen that if you have the poor design of a wind turbine blades, then it may happen that it may not generate the electrical power, because the design or the shape of the blade, that is exactly known as geometry of the blade. So that is very much important in case of design of a wind turbine. So these much of parameters, and that too characteristics of the wind turbine is again a very important parameter deciding the output power out of a wind power system. So the shape of the cross section of the blades, as I already said, this known as aerofoil, and this affects the turbine characteristics very much. We will see in the later slides the characteristics also. Then when we mathematically calculate the electrical power out of a the wind turbine, we usually use some blade element momentum method. Actually, this is nothing. This if we cut a blade, wind turbine blade in various sections. Let's say a complete blade is there, one blade is there, and we are cutting it in, let's say, 10 sections or 10 parts on vertically. I mean, so if we have cut that blade in 10 sections, so each of these section create their own momentum. So definitely, since it is rotating, so definitely each of these section will create some momentum, and ultimately that momentum creates some torques. So this element is nothing. This element is showing, the element means the part of that blade. So if all the momentum of various elements of the blade is sum up, then that ultimately gives the total torque being created over the shaft of the turbine. So that's why this method name is blade element momentum method. So whatever the momentum created by every element, that has to be added first, and then it exactly gives the electrical power out of, or the mechanical power, which ultimately converted to the electrical. So this method will be used to estimate the output power out of a wind turbine. So then here, if you talk, as I already said, that the wind turbine characteristics is very much important when we discuss about the power output of a wind. So that's why a mathematical empirical formula for the power out of a wind turbine is something like this. It is half of rho A Cp lambda beta and then V wind cube. So it is very much conventional for the electrical people, but since so it exactly, what exactly it shows, that it directly proportional to the air density. Rho is the air density, A is the cross-sectional area of the cross-section, or I must say A is the area swept by the wind turbine blades. So whatever is the circle area swept by the wind turbine blade, if it is higher, obviously the power delivered will be higher. And the Cp is very much important, and that depends on the design of the blade, turbine power coefficient, which actually depends on tip speed ratio lambda and then pitch angle. And definitely it is directly proportional to the cube of the wind speed. So it is very much dependent on the wind speed, which is very much I mean obvious that it always depends on the wind speed, and that too very much higher. It is directly proportional to the cube of the wind speed. So here the Cp is very much important, as I already said, and it actually decides by the design of the blades. In general, a typical turbine power coefficient is something like that. It is again has been created by someone, one of the a researcher who actually made the generation of power from a wind turbine, and then draw that with respect to some lambda. Lambda is tip speed ratio, which is given by this one, and accordingly, once they have created the data and plot some curve, then ultimately out of that curve they have fitted some mathematical function. So it is kind of curve fitting way. So through the curve fitting way, the experimental data has been converted into the mathematical form. So actually this is nothing, the Cp formula is nothing, it is the formula which actually found out through the curve fitting way, or you can say by simply correlation kind of thing, where this lambda is nothing. This lambda is the tip speed ratio, which actually one of the parameter. So that depends on the ratio of speed of the tip to the wind speed. So ultimately, if a wind turbine is once it has been designed, then the radius will remain constant, and if the wind speed is also constant, then this tip speed ratio lambda is nothing, it is simply the turbine speed only. So this is the wind turbine characteristics. Now if we draw it, here you can see the drawing of the turbine power coefficient. So although these are very much again conventional, but we should discuss here these two curves also. So here this one is the turbine power coefficient with respect to the tip speed ratio. One can think of that if the pitch angle is 0 degree. Pitch angle means whatever the angle being made by the blade orientation with respect to the flow of wind. Since the flow of wind is always directly perpendicular to the rotation of the blade, definitely always it always happens that whatever is the plan of rotation of the blades is there, the wind speed always will be the perpendicular to that one. So if it is totally perpendicular, then we can think of that beta is 0 degree, because actually this angle, pitch angle, is to be considered with respect to the 90 minus theta, 90 minus the angle between the blade and the direction of wind actually. So if the angle is 0 degree, then it can create highest power, maximum, I mean maximum power. But although that depends on the tip speed ratio, or I mean the generator speed or turbine speed, this TSR, tip speed ratio, is nothing. If you are thinking that the wind speed is constant and then R is, I mean the radius of the turbine is also constant, then this tip speed ratio is nothing. It is simply the turbine speed only. So with respect to the turbine speed, you can think that the turbine power coefficient is something like this. I am talking about this blue one first. So it has a higher value at a specific TSR, or I mean a specific turbine speed. So at the maximum, the turbine speed at which the maximum power is being extracted, or the maximum turbine power coefficient is there, that is known as optimal turbine speed. So every time you can see, you can look onto the curve, that every time that the optimal turbine speed will be different for the different angles. Since if beta is 0 degree, then the optimal uh, turbine speed is something here. And then again, let me put the cursor over here. So I hope it is visible. Let me make the pointer. Yeah. So at beta equals to 0 degree, you can see that where I have put my pointer, this is the corresponding to this value of Cp. Here will be the optimal turbine speed. Similarly, if beta is 5 degree, then there is a different optimal turbine speed. Similarly, if beta is 10 degree, then again there is the different value of the turbine speed. So what we need to do, so we need to control the turbine speed, that is actually on the x-axis, so that we can have the maximum turbine coefficient. Since this output power out of a wind is directly proportional to the turbine power coefficient, so definitely we should have something, or we should have some kind of control which actually gives the uh, which actually runs the turbine at an optimal speed, so that we can have the maximum turbine power coefficient, so that we can extract the maximum power. So the maximum power control is nothing, that actually tracks the turbine speed in such a way that it always keeps the turbine power coefficient at highest value. So every time if the beta is 0 degree, then the turbine speed must be this one in on the x-axis. Similarly, if the beta is 5 degree, then this one, then 10 degree and 15 degree. You can think of that it is changing every time with the pitch angle. With this, we can also see here in the right curve that it is also changing with the wind speed. So if the wind speed is lower, then the optimal turbine speed is something here. This turbine speed is there. It's something 0.5 and let's say 0.7. But if it is 9 meter per second, then it comes out to be zero point 0.8. Then if it is 10 meter per second, then it may be some, let's say, zero point 0.9. Similarly, if it is at 12 meter per second, then it should be, let's say, 1. So every time whenever the change in wind speed is there, definitely sometimes there may be that wind speed will be 12 meter per second. Sometimes it may happen that it will be 8 meter per second. So and again it may be again on next moment it may be let's say 10 meter per second. So the wind speed is changing every time, and that is not in our hand. So what we need to do, we need to have some control which actually track this generator speed, or I mean turbine speed actually. So one of the controller must be present who will uh, track this turbine speed, so that it keep the power coefficient it is its highest value, so that we can extract the maximum value. One important and interesting thing you can find out from here, that how the turbine power depends on the wind speed. So let's say we can think of that for a 12 meter per second, let's say wind is blowing at 12 meter per second. So if the turbine speed is, let's say, 1 per unit, then and then only it gives the maximum power. Now, if someone is thinking that if the turbine is rotating at higher speed, then it should create a higher value of power. That is not like that. It may happen that if a generator, if a turbine is rotating at very fast speed, that means that it doesn't mean that it is giving the maximum power. It may happen that since in case of 12 meter per second wind speed, you can see or the blue curve. Let's say if the turbine is running at 1.5 per unit turbine speed, so corresponding to 1.5 turbine speed, you may see that it is generating only this much of power, and it is about zero point 0.4 only. So it is turbine power is zero point 0.4 only. Even then, wind speed is 12 meter per second, and the turbine speed is 1.5 meter per unit. So, so actually, this what exactly this curve is showing. So this curve shows that it doesn't mean that if a turbine is rotating at very high speed, that means it is generating very much power or higher power. It doesn't mean. It is not like that. So every time a generator or a turbine must rotate at its optimal value so that it can give the maximum power. So now how it happens? Because the speed of the turbine is not in our hand. We can't control the turbine of the speed of the turbine because wind is not in our hand. So what we need to do, we need to provide some control from the generator side. We can have some loading mechanism over the generator, so that generator can basically put some effort on the shaft so that the speed of the turbine may change, and that has to be make on a value of optimal value so that it gives the maximum power. So this is very much important if someone is thinking about the MPPT, maximum power point tracking controller. So that is all about that one. So so the is if you think about the maximum power of the wind turbine, it is at a specific turbine speed, and thus that the MPPT comes into the picture to capture the maximum power from a wind turbine. So every time if you wish to get the maximum power out of a wind turbine, then you need to operate that turbine at its maximum power points. That power points actually nothing. These power points are on these curves only. The points which are at highest value in these curves are maximum power points, nothing more than that. So this is about the characteristics which actually shows the maximum power extraction out of a wind turbine system. So here is the practical reason of working of a wind turbine. In general, power is being generated in between the cut in and cut out wind speed. Not cut out. Yeah, cut out, cut out. So in general, a wind turbine practically operates in between the cut in wind speed and cut out wind speed. So if the wind speed is lower than or this cut in wind speed, then the power will not be there because the rotation of the turbine will be very much slow, and we can't extract the power out of the turbine. And similarly, if it is more than this cut out wind speed, let's say sometimes it may happen. Is there anyone? Is there anyone wish to ask something? Okay, good. Anyway, no problem. So if anyone wish to ask, they can directly ask you. Please mute yourself. Actually, someone is, I think, have unmuted themselves. So a wind turbine always operate in between the cut in and cut out wind speed, and it's rated actually nominal wind speed gives the maximum power. Please make yourself mute. Someone is, I think. Okay, let me. Is there someone wish to ask something? Okay, good. All right. I hope I have muted. So this is the actual practical operation of a wind system wherein it operates always in between the cut in and cut out wind speed. So if there is sometimes it may happen that there is some kind of a storm or kind of dunes are there. So because of that, there may be it may happen that the speed of the turbine, that is, it may happen that turbine speed may go beyond this 1.5 per unit. So in that case, we need to adjust the pitch angle in such a way that it should maintain in between or below the cutout wind speed, because it should not run out of this cutout wind speed, so because it may cause some mechanical failure of the turbine. So that's why it should operate before the cutout wind speed. So as I written here also, before cut in wind speed, there is no power generation, and maximum and rated power generation at nominal wind speed and at cut out wind speed, the generator turbine need to be disconnected. And it generally happens in practical that if there is the storm kind of heavy dunes, then in that case we need to disconnect that wind power generation system from the grid. So this is the actual practical operating reasons of the wind turbine. So now coming to the, as we have discussed about the electrical power out of a mechanical power, which basically comes out from the rotation of the shaft. So that depends on very many parameters. We have discussed about the characteristics. That's why. So now coming to the, what are the various kind of generators which are actually used with the wind power systems, so that we can extract the power out of them. So as I already said, there are three kind of generators which actually integrated or decoupled with the wind turbine to generate the electrical power. First one is very much conventional squirrel cage induction generator, which actually is nothing. It is kind of an induction motor only, and that induction motor, if so from anyone who are from electrical side, they might be knowing that if an induction motor runs more than the speed of synchronous speed, then that will work like an induction generator. So that is the feature here. A squirrel cage induction generator will work here. So if we are designing the squirrel cage generator, this first one, the this squirrel cage induction generator is designed in such a way that it should have lesser value of the synchronous speed, so that the and the gear mechanism is something like that. The speed of the shaft of the rotation of the turbine is always greater than the synchronous speed. So in that way it generates the electrical power. So this is kind of induction motor only. If the speed of the turbine is lesser than the synchronous speed, then it takes the power from the grid. Here this is the grid, here is the grid connection of the wind power generating plant. And in case of an induction generator, it always lacks by some reactive power, so we need to feed some reactive power to the generator. So that's why this is capacitor bank which actually feed the reactive power demand of the generator. So this kind of generator, I mean squirrel cage induction generator, is there, then at that time the speed of rotation of the turbine shaft should always be greater than the synchronous speed. So this condition must be satisfied, then and then only it can deliver the power to the grid. So this is the one of the problem also. Let's say if the wind speed is very low, so in that case the turbine speed will also be very low. So if the turbine speed is very low, then it may happen that the speed of the shaft will be lesser than the synchronous speed. So if it happens that the speed of the generator is lesser than synchronous speed, then it will try to get the power out of the grid. It will absorb the power from the grid. So this should be taken care of, that whenever we are uh, connecting this generator, then the speed of the shafts must be greater than the synchronous speed. So this is one of the problem with that. And these kind of generators can only be placed where the wind speed is almost constant, and it has some higher value, because we need to run the turbine at higher value, higher than the synchronous speed. So that's why. So then the second one is the one of the popular choice of generator. This is the generator for the generation of electrical power through wind, and this is DFIG, or sometimes doubly fed induction generator, or DFIC. So actually this generator is something like that. Its stator is directly connected to the grid. So this is the grid, and here is the, let's say, transmission line, a simplified way. And the stator is directly connected to the grid, while one interesting and important thing is that there are some connections available at the rotor of this generator also. Now someone may think that how can you connect a rotating generator, how can you connect a wire to a rotating generator? So so it is actually, if someone is there from the electrical side, they are knowing very well that we are having some kind of brushes and shaft brush and commutator arrangement. So these brushes will always run over the discs which are actually coupled with the shaft of the generator. So through that way we connect to the rotor conductor through the rotor side. So this may happen with the DFIC only. So it is kind of a squirrel, I mean not a squirrel cage, it kind of slip ring kind of induction motor only, or induction generator only. So we can feed some voltage through its rotor side. So now someone may think that why we are using this AC, DC and this AC converter. As you might be knowing that since this WFI induction generator is also an AC generator, so it injects the AC power to the grid. So there is no problem. And one more thing is that the frequency of the generation of this generator is always as same as the grid. Now, since AC voltage is there at the connection of the wind over the grid, so that is the AC available. So that AC need to be first converted to the DC and then DC again converted to the AC. Now, why this need of this generation of this AC here to inject it to the rotor of the shaft? So some of you might be knowing that the frequency of the voltage which are there in the rotor conductors, there are two kind of voltages: stator voltage and then rotor voltage. So that rotor voltage current, frequency of the rotor voltage, current and voltage depends on the slip of the that generator. So now here the slip is again one of the another thing which actually the difference of the synchronous speed and actual running speed. So accordingly, the frequency of the rotor voltage is always a very few hertz, let's say 4 to 5 hertz only. Even then, if you think about the stator voltage, then it will be 50 hertz, because in India we are having the frequency of about 50 hertz. So stator voltage have frequency of 50 hertz, but the rotor voltage have the frequency of only 4 to 5 hertz, right? So that much of frequency, I mean 4 to 5 hertz, we need to have some kind of inverter which actually converts the DC into the AC and then gives the voltage of about 4 to 5 hertz. So that's why we need to put these mechanism, to back converters, which actually converts AC into first DC and then DC into the AC. So actually what happens with these kind of generators? Actually, the important thing with the DFIs is that it can inject the power to the grid through its stator as well as its rotor also. Although the power injection through the rotor depends on the speed of rotation. If it is rotating, if this generator is rotating more than the synchronous speed, then it can deliver the power to the grid from both the sides, stator as well as rotor. But if it is rotating at synchronous speed, then it can deliver the power to the grid through stator only. There is no power exchange through the rotor. While if its speed is lesser than the synchronous speed, then it takes the power from the rotor side, but it actually delivers the power to the stator. So this is the important thing which actually happen only and only with the DFIG. Although, as I already said, that we can't operate this generator, that means the squirrel cage induction generator, below synchronous speed, because at below synchronous speed it will try to takes the power from the grid rather than giving. So while in this case, it can deliver the power in all kind of wind speeds or all kind of turbine speeds. It can deliver the power at the synchronous speed, above synchronous speed, and below synchronous speed. And accordingly, we usually say that the DFIs is operating at synchronous speed or synchronous operation, sub-synchronous operation if it is below the synchronous speed, and super synchronous speed if it is operating at above synchronous speed. So accordingly, three kind of operation will be there, and all three kind of operations, this DFI is always delivered to the power to the grid, even if the speed is very less than the synchronous speed, then also it can deliver the power. So then next way, that is third one, which actually sometimes utilized, but if a wind plant of lower scale, I mean some kilowatt kind of wind power plant is there, then these kind of generators are there, because since this is permanent magnet synchronous generator, so these kind of generators have their permanent magnet, its rotor, and stator is directly injecting the DC power to the grid. So okay, it is, since it is synchronous generator, so it delivers the power here, it gives the power, but the frequency of the voltage which is available at here where I have put my pointer, the power available at the place of pointer, which I have put here, you can see, I think, at this place, the frequency will be varying. Why this is varying? Because wind speed is not in our hand, and that's why the speed of rotation of turbine is also not in our hand. So it may changing. So because of the change in the shaft speed, the frequency out of the synchronous generator will also change. But that varying frequency AC voltage can't be feed to the to the grid, because we need to take care of the power quality also. Varying frequency AC voltage is very much poor in the sense of, in the case of power quality. If you talk about the power quality, a good quality power must have constant frequency voltage. So that's why, so this AC has to be first converted into some constant DC value, and then that DC converted to the AC with a fixed or a constant frequency voltage, which is to be injected to the grid. So that's this is the way wherein the synchronous generator, and that too permanent magnet synchronous generator, feed the power to the grid. So this is also very much not prominent. Why? Because here the power which is being generated through the generator, this total power will flows through the converters, because these converters has to handle this much of power which actually being generated by the generator. So in that case, the size of the converters will be very much big, because the size of any electrical equipment depends on the handling capacity of voltage and current. If you need to handle more and more current or voltage, then the size of equipment or the size of component will definitely be big. So in here, this is the one of the problem, that the converter need to handle full amount of power. So that's why it is also known as full converted synchronous generator. Why full? Because the full amount of power which is generated through the generator will be passed through this converter circuit. That's why. While in the DFIG case, it is not like that. Here, maximum power is being fed through the stator. About 70 to 80% is powering is being delivered from the stator, and also, while a few amount of power will be delivered through the rotor side. So here in this case also, the size of inverter or the size of converter will be very lesser. Why? Because there is a lesser amount of power being exchanged through these converters. So these are the various kind of generators which actually used with the wind in general, in practice. While most of the megawatt rated wind power generating plants, these kind of generators are there, WF induction generators, because there is the flexibility of the control. We can put some control over the inverters or the controllers to inject the voltage to the rotor of the generator, and then rotor can this voltage, output voltage of the generator, the shaft speed can be controlled through the control way from the rotor side. So that's why this is very much conventional, I mean prominent, and in general use in the industry. So that's why I am talking about here onwards. I am talking about the WF induction generator only, which actually used in general. Please, is there anyone who is talking? Wish to ask something?
Yes,
Please keep
sir. Sir,
yourself mute,
sorry
or
to
if you
interrupt
want to
you.
ask something, I can answer
Yeah,
them.
your screen was just fixed. Now it is changing.
Oh, maybe there is some problem of internet at your side. Since is it okay? Maybe because
Sir,
of the full.
now I can see the modeling of grid connected
Yes, yes,
DFIG
exactly.
wind.
Yeah, yeah. I am
Okay.
here only on this slide only.
Yeah, yeah.
Okay, thank you.
Okay, thank you, sir.
So, since as I already told in the last slide that out of the various kind of generators, this DFIG kind of generators are mostly used, and these are the prominent in most kind of wind industry. So that's why I am discussing here onwards about the DFIG only. So as I already said, this is kind of structure is something like that. It is very much in a single line diagram way. So this is the turbine, and then here is the gearbox which actually increase the speed of the shaft, and here is the generator which actually feed to the grid. So as I already told that the stator, this generator can feed the power from its stator as well as its rotor. So that's why its name is doubly fed, because it can feed the power from double side, stator as well as rotor. So that's why it's known as doubly fed. Two sides feeding can be there through this generator, although it is a induction generator only, and that too of slip ring induction generator, but it can feed the power to the grid through two sides. That's why it is known as doubly fed. So as I already said, the DFIs is a wound rotor or a slip ring kind of induction generator with slip rings to take current into or out of the rotor winding. We can inject some voltage to the rotor and we can take out of the voltage from the rotor. So which actually enable us to make the controls over the generator and the turbine and all. The stator of the generator is directly connected to the grid, as I already said, to the grid, whereas the rotor is connected to the back-to-back converters with a DC link in capacitor in between. So the use of this DC link capacitor in between these two is, I already told that this capacitor is nothing. It is simply making the DC voltage constant. So that's why it is present here. And as I said, that can feed power to the grid. It's from its stator and rotor both way, and that is why it is known as doubly fed induction generator. Now, the interesting thing which actually happened with the doubly fed induction generator is that here you can see in the converter network, this is the main control way through you can control the output voltage, active power, reactive power, kind of speed. Everything can be controlled through the rotor side converters. These are the converters which are present in the rotor side. So there are two converters: machine side converter and another one is grid side converter. Since this side is grid, so that's why grid side and machine side converter. So by making some reference value uh, in the torque or the power in the machine side converter, we can control the active power out of this generator. Similarly, if you are having some reference value regarding the stator voltage, then we can control the stator voltage also out of this generator. Similarly, reactive power and the DC link voltage can also be controlled through these two converters. Now, how can we how can we perform the control using these converters so that it can track it reference value of torque and then supply this stator voltage as well as rotor reactive power and DC voltage. So these will happen through the PI controller, which is very much basic. With the help of PI controllers, we can make some arrangement in such a way that it can deliver the power it in a controlled way. So accordingly, we need to design the control. So now coming to the various controls, as I already said, the machine side control and grid side controllers are implemented in its rotor circuit. So actually both the converters do nothing. They simply make the change in the rotor voltage, and accordingly we can get the desired control out of that. So rotor side converter controls active power and stator voltage, similar to the exciter in the synchronous generators, whereas grid side converter controls the rotor reactive power and DC voltage, DC link voltage. In our case, we have make such an arrangement that we are making the active power control, reactive power control, then stator voltage as well as the DC link voltage control. So here we are putting in the this one, we are putting four kind of controls simultaneously. So actually, let me see that whether it is shared properly or not. Okay, it's fine. I was talking that there are, this is very much conventional, and we are putting four kind of controls. Four references are there that need to be tracked. So that's why these two controls are from the MSC side, that is machine side controller, and through grid side controller, we are putting the control over the reactive power and DC link voltage control. So accordingly, as I said, that the electrical power produced is the sum of the total power, that is stator and rotor power. And the stator power is okay, but the rotor power depends on the speed of the generator. If its speed is higher than the synchronous, then it operates at super synchronous, and if it is operating at lower synchronous speed, lower than the synchronous speed, then it operates at the subsynchronous operation. So in general, if we mathematically implement the control or design the control, we need to have the mathematical model equations of the turbine, then see here in this picture, we must have the mathematical model equations of this turbine, and then we should have the equations of this gearbox, then we should have the equations of this generator, and definitely the equations which are associated with turbine or gearbox or generator, that always have some common variables. Definitely common variables will be present, because through that common variables only these mathematical equations will interact to each other. Similarly, this generator is also integrated with the grid, so obviously these grid equations will also be integrated, or the variables associated with the grid equations will also be present in the generator, and in the equations of the generator these grid equations will also be present. So that kind of coupling will be there in between the mathematical model. So through that, I'm just also I'm just skipping the mathematics, but since, as I already told, that these components must be first mathematically modeled. So here is the first: wind turbine and drivetrain. Drivetrain means the gearbox. So since the inertia of, as I already told about this wind turbine, that the power, mechanical power or the aerodynamic power out of a turbine is simply that half rho and then area and Cp and wind speed cube. That was the power. So that can only be modeled by that equation only. Then if we model the drivetrain, that is the gearbox, then since the inertia of the turbine is very much big as compared to the generator, this can you can simply practically think of that the size of the turbine is very big, while the generator, which is actually coupled with its shaft, is very small in size. So definitely, if a higher or a big size of mechanism is there, then that has higher inertia. While if some device which actually has lower weight or the lower size, then that has lower inertia. So since there is a big difference between the inertia between the turbine and generator, so that's why we need to model it in a two mass model, two separate masses. One mass is of turbine and another mass is of generator. So accordingly, we need to have the dynamic equations. So these are the power balance equation. Yeah, here turbine speed balance and then generator speed balance, and this is the shaft twist angle theta TW. So accordingly, these balance equations will actually make the generator in equilibrium position. So these are the power balance equation, nothing more than that, where this turbine speed decided by the turbine torque and shaft torque, while the generator speed decided by the shaft torque available at the shaft, and then the electrical power which is being fed from the grid. How much, if you are getting more and more power, then this electrical torque will be higher and higher. If that generator is not feeding any of the power, then this T will be zero. And similarly, if the speed of the turbine and generator, so the difference of these will actually gives the twist angle in between the end of the shafts. So here the shaft torque depends on the various mechanical parameter. Ks is the shaft coefficient, then damping coefficient of the shaft and all. And the electrical torque depends on the generator parameters. Here these are the stator and stator voltage and stator internal currents, which actually gives the electrical torque. Then, as I said, that this is P turbine power is nothing. It is the power which I have already talked about, that half rho Cp, and then it has simply been put in per unit only, nothing more than that. Then coming to the generator equations, so these are the model equations of the mathematical model equations of the generator, although I should skip them because these are the balance equation of a generator. If someone is thinking what exactly these equation or what exactly these equations do, so I wish to clear here is that these equations are practically representing a generator, how a generator behaves with respect to the various rotor voltage, stator voltage, and its input power and all. So these equations are the dynamic equation of that generator, and the practical generator will characterize as same as by these equations. So in general, whenever we design some device, we every time we need to have the mathematical equations of that. So these are, so that's why the purpose of these equations are. So I'm also skipping this. Then there is the grid interconnection. As I already said, that generator need to be connected with the grid. So there are in general, simply we can put the Ohm's law, and then the voltage difference between the wind generator voltage and the grid voltage, the difference of that voltage division by the reactance of the transmission line actually gives the stator current which need to be fed to the grid. And accordingly stator voltage will be there. Here VB is the infinite bus voltage. um, since I have considered an infinite bus, the grid has been considered as an infinite bus means a terminal where a constant voltage with constant frequency of voltage is available. So that is generally modeled in electrical or in power system is a infinite bus, that exactly named by infinite bus. So accordingly the active and reactive power are there. Then if we talk about the mathematical analysis, so every time if we making some control or we're designing some control, we need to take care of the stability of that. So in our case, in my case, what I am doing is that I'm taking care of all the equations which are associated with the gear train, then turbine, and then generator. I have linearized them, and then made some matrices, system matrices, which actually reflect the characteristics of that wind power generation system. So accordingly, we come out with the matrix A and B here through linearization, and this can be found by mathematically solve them. And here A is something where F is nothing. F is the set of differential equations which I already explained in the last 2-3 slides. G are the algebraic equations where X is the state variable and Z is the algebraic variable. So by making these kind of matrix A and B through linearization, now the eigenvalues of these A and B matrix will give the stability or the small signal stability. So these stability will actually be reflected in practice. If in practice, if these matrix A and B has some negative, or I must say that if they have the negative damping factor, then definitely that wind power generation system does not work at all. This will happen in practice also, that if the matrix A has, which is exactly coming out of a generator with some parameters, so that will not work at all. So that's why we are making this kind of analysis. So once the matrix A and B have been found, then here is the eigenvalues are obtained out of that matrix. First, we can think of that there are four various kind of eigenvalues comes out of that matrix A. See, you can found the frequency component as well as damping factor of that wind system. See, all the dampings are positive, so that means that generator will work perfectly with the parameters which I have considered. It may happen that if there is some, let's say, the rotor resistance or the stator resistance or the inductance of the rotor or inductance of the stator or the mutual inductance, if there is some change in value, or if there is something not good designed value of L, R, and all, then the damping factor may come out in negative value. So in that case, that the generator will does not work at all. So here the damping is shown with the respect to the frequency also. This is the frequency with 49.87. Actually, it is the frequency of grid only. So then there is one another frequency of 10 hertz. There is one mode of this 10 hertz. Another one is this 0.5 hertz only. So since if we find the participation factors or the participating states through some mathematical way, you can see that these two lower frequency, I mean lower frequency modes are very much dominant in case of the stability of a system. In any kind of system, the lower frequency modes are very much dominant. So here in our case, electromechanical, because the generator voltage, stator voltage, internal stator voltage, and mechanical speed is there. So that's why it is electrical parameter and mechanical parameter. That's why its name is electromechanical. While in the last one, here theta twist is the twist angle of the shaft, and this is the generator turbine speed. So that's why it's these two are in mechanical parameters. So that's why it is mechanical mode. So these two modes are very much dominant. So these will decide the stability of that one. So now, since these are the mathematical analysis, but since if we do the time domain simulation, these I mean these frequency components or the modes will also be present there. So that's why I have done the time domain simulation also. Here is this the time domain simulation of that. Through the MATLAB, I have performed the simulation using some ODE solvers, ordinary differential equation solvers. Here I have put one disturbance of the infinite bus grid voltage, or I must say the grid voltage. I have made some changes with the infinite bus voltage, and then I have removed after some time. So the generator speed and active power. This is actually the active power. Active power will be of the generator will be something like this. Here you can see that if you zoom this one out, and then you will see that there are the all kind of modes which I have already discussed in this one, excluding this fundamental frequency, that is 49.87 hertz. Rest of two frequency, that is 0.5 hertz and 10 hertz, both are present in this time domain. So actually it verify the mathematical analysis through model, that small signal analysis, or through the eigenvalues. So always a practical WFI induction generator also behaves like this one. Always a WFI induction generator which is connected to the grid. When there is the disturbance in the grid, then the speed and the active power out of the generator will always be changed, something like this one. So this actually gives the characteristics of our generator. So all the modes are present in the power subjected to the voltage dip disturbance. So actually what exactly it does, it verifies or it validate the eigenvalues of eigenvalue analysis which you have done in earlier through this time domain simulation. Now here is the time domain simulation of open loop system. As I already told that if you are changing the rotor voltage manually, let's say the rotor voltage if changed it manually, then definitely there will be some change in the output power, stator voltage, kind of rotor voltage and all, rotor reactive power and all. So that's why in that way here I just tested that if I change the rotor voltage, D and Q component of the rotor voltage, then definitely active power will be changed accordingly. Even then there is no change in the wind speed, no change in another parameter, but if you change the rotor voltage only, which actually we are injecting into the grid and then injecting into the rotor of the generator, and that exactly changes the active power output and then turbine power coefficient as well as generator speed. So this what exactly this shows? This shows that by changing the rotor voltage by some way or by some control, we can put the control over the generator of that is DFIC. So by changing the rotor voltage, we can control the generator, and accordingly we can design some control, and the designed rotor voltage will actually control the WFI induction generator. So these slides actually shows the this one. Now coming to the controller part, as I said that the active power and stator voltage has been controlled through machine side converter. So it must obviously have some PI controls. So there are various techniques. Here I have associated with the flux of the rotor, and accordingly this technique's name is flux magnitude angle control, FMAC. Although there are DTC control is also there, direct torque control also, direct power control DPC is also there. But here the rotor angle and the rotor voltage, magnitude of the rotor voltage and angle of the rotor voltage, which ultimately can be converted through PWM converter in VDR and VQR, that is D and Q component of the rotor voltage. So that has been obtained through 4 PI controllers. This is one of the PI controller. Again KP1, KI1. Similarly here this is the PI controller 2, and then 3, and then 4. And the reference value corresponding to the maximum power points has been took here. Here this omega r is nothing. This is the optimal power which I have already talked about. Optimal rotor speed is that speed where the turbine gives the maximum power. So that has to be placed here because we need to get the maximum power out of that. So this decides the maximum power output of the wind turbine system. And here is the stator voltage which I have put here equals to 1. Vs reference as I have put it 1. That means that generator DFIG should work in such a way that if there is any change in disturbance is there, that these two PI control would act something like that. It will keep this V as reference equals to 1. Vs is equals to 1. It means it keeps the stator voltage equals to 1 per unit, this controller, these two controllers, while the another two PI controller 1 and 2 keeps the generator operating at its MPPT points. So this has been achieved through the flux magnetic angle control. Then we can have some another PI control which actually associated with the grid side converter, and they can control the DC link voltage and rotor reactive power control. So I mean, to keep the lesser value of the converter ratings, we are putting the rotor reactive power equal to 0, and then reference value of the DC link voltage equals to 1. And accordingly, two PI controllers are here also. One for the DC link control and another one is the rotor reactive power control. So accordingly, again, we have got some grid side voltage D and Q component. First, we get the angle and magnitude, and then ultimately converted through some PWM converters, which actually gives the VD and VZ, which are responsible for the control of DC link voltage as well as rotor reactive control, rotor reactive power. Here, these are the DC power dynamics, DC link capacitor equations, which actually is nothing. This is the difference of grid power and then rotor power. So difference of these two powers is the power associated with the capacitor only. So that's why this equations comes out. And by associating all these equations, again we are doing the model analysis with the controllers now. Since every PI controller, some people are there from the electronics or some EIC and electrical, they people are knowing that whenever we are putting one PI controller, that always add one more state. State is nothing, it is just a variable which actually gives the internal characteristics of any system. So any mechanical dynamics which is rotating or having some rotating part, that always have some states which are which actually gives the information of that system, internal parts of that system. So that is basically known as a state. So every time whenever we are adding some PI controller, always there is one more state being added with that system. So accordingly, since we have added 4 PI controllers earlier with the active power and reactive power, and then 2 later on for the DC link and rotor reactive, and accordingly we have made 6 these states associated with the 6 PI controllers, then one associated with the DC link, and another these states are associated with its internal structure of the generator, then gear train and turbine. So accordingly, doing all kind of mathematical simulations, we again have linearized it and got the matrix A again, as we have did in the last in open loop control. And again we have found the eigenvalues of the controlled W index generator. And here you can see that the number of modes have been increased now, because by adding the PI controllers, number of states have been added, and accordingly it may has more number of modes. So accordingly we can see that the damping, although its damping is having lesser than the open loop, so it always happen that since we are putting the controllers, so every time if we put some controllers into a system, that always makes it unstable, even more unstable. Or I must say, although it is stable, because here you can see that all the delta, that is damping factors, are positive. So that means that then that DFIC with all kind of controllers is also stable. That's fine, but what exactly is there, these damping values are lesser as compared to the open loop. So that means if we are adding more and more controllers with the any kind of system, that will make it stable, or I must say that is prone to the stable, prone to be unstable. So in a small disturbance may create them unstable, while an open loop control or an open loop without control, that may not be unstable because of a small disturbance. So this is actually giving the characteristics of a controlled W index generator. Here again the time domain simulation of the controlled W index generator connected to the grid. Again, see here, this has the modes of 80 Hertz, then 7.79 Hertz, and 0.53 Hertz, which are actually also present in here. See here, this is 80.31, 7.79, and again 0.53 hertz. So this is actually validating the time domain simulation. So this is the actual characteristics which is happening with the real generator. If a WF induction generator connected to the grid, there is a disturbance into the grid, then the generator speed and active power and terminal voltage. See, this terminal voltage is, I mean, it is coming to zero for an a small time. It is about 1 to 10 to 10.2 seconds. So for zero point 0.2 seconds, it comes out to be about zero. Then since because we are having the controller which push this terminal voltage again near to 1. Why? Because we have put one controller which actually try to keep this generator working at its one value, or per unit value, one value, 1.0 per unit value. So here is also one more investigation with the change in wind speed. So if the wind speed is from, let's say, 12 to 12.5 meter per second, or if it is from 12.5 to 12.75, and 12.75 to, let's say, 12.25 meter per second. So if this kind of wind speed is there, the turbine speed will be something like this. So as we have already put here in the maximum power point tracking control, or the reference power control. So that's why as soon as the wind speed change, the turbine speed will also change, because we have put the controller, and it will keep tracking the optimal value of the turbine speed. This is the optimal speed. As I already said in the turbine power coefficient curve, that for a generator which is operating at maximum power point tracking point, it should always track the optimal value of the turbine speed. So here the blue curve, this is actually tracking the optimal value. This red one is the optimal values with respect to the wind speed. So as soon as wind speed changes, the optimal value of the turbine speed changes, and accordingly this blue one is the real value, which actually keeps on tracking that optimal value of the turbine speed. So this actually shows that our MPPT controller, which basically incorporated with the generator, is working perfectly, since it is operating the generator at its maximum values. Here is again some power during MPPT, although the power will also be there. So this is the turbine power coefficient. It will be maximum value per unit value. While whenever there is the disturbance in the wind, there is a small change in the power coefficient will happen, because during that transition from lower to higher, or higher to lower wind speed, that during that transition generator speed will not change immediately, because generator itself has its own inertia, so it takes time to change its speed. So that's why this spike is there. And the power output from a wind power generator is something, this magenta curve. So that depends, since we are increasing the wind speed from 12 to, let's say, 12.5, that's why it is increasing from here to here and then here to here. If we not put this MPPT controller here, then it may happen that it may not reach this value. Similarly, it may not reach this value. Similarly, this may also not reach this value of 1.05 value if the MPPT controller does not, does not working or not present in the controller side. Then here are again the DC link voltage control way, as we have put it around 1. So these controllers tries to make it around 1. Similarly, rotary active power, we have put the reference value 0. So that's why subjected to the disturbance, immediately these controllers work and it makes it again 0. Similarly, the state terminal voltage is also there. Also there is the spikes in the voltage, but since we have put the controller for the stator voltage, so that's why it is keeping it on 1 with the change in the wind speed. So this is the simulation with the turbulent wind. If the wind speed is changing very rapidly, so here it is of 200 seconds wind speed data is there. These are the data of real wind speed, and these because of these real wind speed data, the generator speed will be something like this. Obviously, if there is the change in the wind speed, the change in the turbine wind speed will also happen, and accordingly, here you can see that around 50, or here at this point, wind speed lesser, so that's why generator speed is also lesser. If it is at higher value, let's say here this is the peak, so that's why this generator speed is also at higher value. But at the same time, our MPPT controller is also working. So every time, whenever there is the change in wind speed, every time that turbine power coefficient will have some spike, because as soon as wind speed changes, the turbine will not change its speed immediately, because that has its own inertia. So it takes time to get near the optimal value. So that's why these spikes are there. If we can imagine that if the turbine or generator does not have inertia, then what happen? Then the CP will always remain constant or always remain one only. But since these have inertia, so that takes time to reach again at maximum power point. So that's why there is the change in the value of that turbine power coefficient CP at the last curve here. Then this is the last, content, which actually, although it is not much advanced, but one of my IET journal, I have got one journal article out of this work, and this is the damping control through linear quadratic regulator. Although this is not very much um, conventional nowadays, it is about 5-6 years back. I have did in during my PhD. So there is nothing new in this. Actually, what I did is that uh, some of you might be knowing that this linear quadratic regulator is a kind of state feedback controller, wherein all the states can be fed to that controller, and then it generates some output voltage. So earlier what we are doing, these two back-to-back converters are there, and the rotor voltage are being controlled through some reference value of active power and stator voltage. But here in this case, what we are doing, what we have did, what we did is that we takes all the states of the all of this wind power generating plant, and then makes some state feedback control u equals to minus kx. So that k is basically coming out from some optimal way of energy. So whatever the total energy of the system always depends on the states. Let's say if a system has 5 states, then the total energy of that system is always equals to some states square and then integration with respect to the time. That comes out to be one cost functional. Actually, that is known as cost functional. Some of you might be knowing that cost function is nothing. This is the kind of energy which actually that complete system has. So in our case, the all the states and then squaring of that gives the total energy, and that has to be some way optimized. And in between, there is one equation which actually coming out uh, during the minimization of that energy, and that equation is known as Riccati equation, ARE, algebraic Riccati equation. So that algebraic Riccati equation actually gives the control output. So here the important thing is this LQR controller only. What we are doing, we are feeding the states here in, and then the rotor currents as a measurement, and then giving the rotor voltage out of it. These rotor voltage are nothing. These are being fed to the generator of this DFIC actually. So these rotor voltage which are coming out of this controller fed to the rotor of the generator, which actually controls this generator to make it damp. So this is actually the basic theme. So what exactly the basic theme? We are simply designing the rotor voltage in such a way that it damps the oscillation of the generator. It may damp the all kind of, since it is we are feeding all the states, so it damps all the states. So definitely, because all these states are associated with the active power, reactive power, stator voltage, and then the voltage power associated with the rotor also. So whenever there is the change in the all these states, definitely that comes out to be sometimes, let's say, k and multiply of that. So they exactly gives the rotor voltage which to be fed into the fed into the rotor of the generator, and by that this generator get damped. So here is the scheme. Actually, the basic scheme or basic theme behind this one is there. So here is the mathematical way of that. This is nothing. This is the mathematical model of the wind power generation system, linearized model of that. and we are having this much of LQR, linear quadratic regulator, wherein one internal matrix P is generated, and then this state feedback gain comes out from the algebraic quadratic equation ARE, and ultimately this here you can see that here is the delta x and here is the delta u. So delta u is equals to minus kx, nothing more than this. So this x, what is this x? This x consists all of the states of the mechanism or all of the systems of the states. So one important thing is that since we are using these internal voltage of the ED dash, EQ dash, these are the internal voltage of the generator, and the uh, getting out of these voltage from the generator is not much easy. Along with that, there is the twist angle. Also, the twist angle is measurement of this twist angle is also very much not much easy. So what we need to do, we are simply estimating all these. So instead of using the real values of them, we are simply estimating all these values. So in that way, this estimation has been performed by unscented Kalman filter, which actually takes some measurement, then takes the dynamic equations of the system, and then there is the measurement model. So through that, it estimates the value. So instead of getting the direct value of these states, we are estimating all these values and fed to the linear quadratic regulator, which ultimately gives the power out of that. So this way we have we have designed this control delta u equals to minus k delta x, which actually gives the delta u is nothing, the rotor voltage, which actually fed to the rotor of the generator for the damping control. So it has also been compared with the PSS, which is very much conventional power system stabilizer, and so the if you are adding these kind of PSS, so the PSS also has a kind of washout block, lead lag compensator, and accordingly we are adding more and more number of states. So accordingly x8, x9, x10, these are the states mathematically have been added into the mechanism or the system. So here is the states with respect to the addition of LQR. Here without LQR, when there was no control of LQR, then delta was 0.03, 0.13, then 0.09. So these are the values of damping factor. So definitely if we add the LQR control, then definitely these delta must be improved. And then only be the benefit of this LQR. So that's why it has been made the eigenvalue analysis or the model analysis has again been made through with the LQR control or linear quadratic regulator control. So it can be seen that some of the dominant modes like this one, mode 2, you see this is 13%, while if it is we are adding this state feedback control to optimal control, linear quadratic regulator is nothing, it is an optimal control, it is making double of the damping, so it is improving the damping. Similarly, if we think of this one, lower frequency mode, then it is also from 9% to 47%. Similarly, if the grid is very weak, then it may sometimes happen that the system may become unstable, since it can be seen that here is the minus of damping. So in this case, the generator will not feed to the grid or not work at all. So with the help of LQR, this may improve, and it has been improved from minus 0.6 to the 5%. So if there is the LQR controller, then it will work perfectly. Similarly, it has again this mode has also been increased from 9% to 47%. So with the addition of this linear quadratic regulator, this controller, with the addition of this controller, the WF induction generator will effectively work even then if it is connected with the big grid. While if it is weak grid and there is no LQR control, then it may become unstable and it will not work at all. So that's why this is the purpose of this linear quadratic regulator. So now here is the time domain analysis. Again, although these are the uh, performance of the estimator, that is UKF, wherein you can see that the actual value and estimated values are almost matching. It shows that the estimator is working perfectly. Then here you can see that the without control there are the more oscillations, blue one, while if you are putting the PSS control, which is very much conventional, it damps the oscillations, but in some extent. While if you are having the linear quadratic regulator, so it damps the oscillation more, as well as at the lesser amount of energy. So since the concept behind the design of this LQR controller is the minimum use of energy. So there are two benefits. One is that it is damping perfectly, one thing. Second thing is that, and that too with the very lesser amount of energy or lesser amount of rotor voltages. So these two are the benefits out of this control. Here is the cost, or I must say the value or the energy which is being fed to the rotor voltage for the control of that generator. See, in the case of LQR, it is lesser. All the time it can see, you can see if the voltage dip of around 10%, 20%, 30% in every case. And then even if the change of the wind speed also, every case it is lesser with respect to the LQR, while it is higher in case of PSS, power system stabilizer. So again, these are the results of the rotor voltage in case of LQR and PSS. See here in with the PSS, it is higher value, red one. But if you are using a linear quadratic regulator, it is very lesser value. So we are using lesser amount of energy with a good damping efficiency. So this is the benefit of this proposed optimal control. Here is the ultimate conclusion. Since we have discussed from the very basic characteristics of the wind turbine, and then later we came to know about conventional control of the controls of the WF induction generator, and before that what are the various generators being used with the wind systems we have discussed. And then model analysis, that is exactly the eigenvalue analysis for the stability of a wind power generating plant is there. And lastly, we have discussed about the uh, damping of damping of the wind power generating system using some optimal way, that is linear quadratic regulator. So this is all about my presentation. So these are my references which I have considered during the research. So if any of you have any question, they can directly ask on any of the slide and all. So I think the time of session is also going to be over, and I hope Professor Sathan sir will be there to take the next session. Since I have just completed, I'm not sure that sir has joined or not. Let me talk
Sir,
to.
he has joined.
Okay, okay, all right. Thank you. Silpa, are you there?
Yes, sir. And sir, your session
Okay, okay.
was very excellent and informative. You have very
Okay.
well explained.
Okay, thank you very much. So before starting the search session, and if any of the participant has some question or they have any kind of doubt, all those I have started from very basic and try to explain the damping control which I have implemented through that linear quadratic regulator, that exactly is in optimal control way. So I have tried my best, and if even if any one of you have any question, they can also write me on mail also. And one more thing is that if someone have missed this recording will be available over the YouTube. We will, once this course will over, I'll upload all the sessions in the YouTube, and you may find there also. So with this, I am winding up my session, and let me stop the sharing as well as the recording also.